example, quantum field theory 1 and 2. So I'm not going to do those things. My target group would be undergrad, say. So I will not go into the mathematical formulation of group theory, but I will try to convey you the message without using much mathematics. So in this talk, you are going to learn about a few things. Okay. So you will see why, for example, electromagnetic waves exist for all wavelengths, right? We never wondered why there is X-ray, why there is gamma ray, why there is visible light, microwave. For all wavelengths, they exist, right? So then you might even ask a more deeper question: why light or electromagnetic waves should exist in the first place? Why is there light? Or why is there sound? Why do we hear sound? Why sound waves exist? Or why even gravity exists? These are very fundamental questions, and I will show you that through the understanding of symmetry, you can shed light on these deep questions. Or even why there should be some conservation laws like the conservation of energy, why it is there. And if you meet some alien over a telephone call, can you explain to him what is left and what is right? Is it possible to do it? Or say, why in superconductors magnetic fields do not enter? So all these things can be well understood through the concept of symmetry. So part of it will be very advanced, and I don't expect all of you to go along with me all through, but slowly I will answer all these questions. So as I already said, the rigorous understanding of symmetry comes through the understanding of group theory and courses on quantum field theory. But for non-experts, I give some pop references here. There is a symmetry article in Wikipedia. There is a video in YouTube on what is symmetry in physics. There are very nice Feynman lectures, and one of them is actually on symmetry in physical law. I ask all of you to watch this video because Feynman lectures are always good. And then there is also a video called Beyond Beauty, the predictive power of symmetry. This is also a nice one. And finally, there is this Stanford Encyclopedia of Philosophy, which is also a good read that talks about symmetry and symmetry breaking. So these are all for non-experts. Now, I would like to start with a philosophical point of view and then go into math. I will try to convince you from a philosophical perspective why symmetry is good. What is symmetry to begin with? In simple language, symmetry is a change that does not make a change. It might sound a bit weird to you, but look, here is a photograph of a famous person, and whenever you talk about symmetry, the name of this person comes to your mind. This is none other than Amy Noether. And look at her face. Her face has a bilateral symmetry, left and right. Approximately human face, left and right, they look similar. They look like a mirror reflection of each other, right? So that's the symmetry. Then you have a snowflake. This is actually an original snowflake that has a 60-degree rotation symmetry, and also there are more to it. From an ideal point of view, this also has a self similarity symmetry, but I will not go into that. Then there is a flower which also have some rotational symmetry. Then there is this flower that we have in Bangladesh, this the kodam phul, and that also has a symmetry which is a bigger symmetry than that of the flower I just showed. Then you have the honeycomb, and this has the translational symmetry, because if you take the honeycomb and you make a plane in infinite plane out of it, wherever you go it looks the same. It's it's a translational symmetry. And last, you look at this cauliflower and you take a small portion of this cauliflower and zoom it, it looks the same as the big one. So this is also self similarity symmetry, which is extremely important for the understanding of fractal. And in this talk I will not mention about self similarity much fractals, but that's a very important symmetry of nature as well. So then comes the question, symmetry is beauty actually, right? If not, this lady would not spend thousands of dollars to make a facelift, right? Her face was not mirror symmetric. It was not left right symmetric, and then she went through a surgery and made the face symmetric. Because we human thinks that if you look at a person and if the person left and right are symmetric, more symmetric, we call that person beautiful. And that's also true for the animal kingdom. We look at these birds are called zebra finch birds, and the females, the left one is a female, the right one here is a male that has some orange spot on the cheeks. So when a female wants to choose a partner, it looks at a male zebra finch to see if the bird looks symmetric on both sides. And there is a research article here called "Preference of Symmetric Males by Female Zebra Finches." Because symmetry means beauty, symmetry means health, for both humans and for animals as well. It's not just that this symmetry that the female bird looks can both be artificial and and natural, right? When you put a ring, you see there is a green ring on the leg of this bird. When the experimentalists put rings of different colors on both legs, the female bird will not choose that partner. The female bird will choose a partner when the both legs have rings of the same color. So you see a preference of symmetry here. So why this Taj Mahal looks so beautiful to us? In Persian architecture, in general, there was a huge prevalence of symmetry. This Taj Mahal looks the same when you rotate it by 90 degrees. And here is also something else that has a eightfold symmetry. That's the rooftop of some mosque in Iran. And then last, you also have the Eiffel Tower that also looks the same when you rotate it by 90 degrees. All these things are beautiful objects, and they have symmetry. So, and then we can ask, okay, we have symmetry in nature, but we have also symmetry in the laws of nature, which is physics. And why could it be the case? Maybe the philosophical answer was given by Keats, the British poet, that beauty is truth, and truth beauty, that is all you know on earth and all you need to know. Okay. So
That
symmetry is beauty, and beauty could be related to truth. That's a philosophical point of view.
is truth. Truth, beauty.
Yes. Hello.
May I ask some? Could you please mute your mic, please? All of you, please. I can hear some noise.
Okay.
Thank you. Okay.
Now, the next question is symmetry fundamental? This question was asked by Greek philosophers more than 2000 years ago, and they were so fascinated by symmetry that back then they had these 5 platonic solids that are symmetrical tetrahedron, the red one, octahedron, hexahedron, icosahedron, and the dodecahedron. So they were so fascinated by symmetry, they thought that the fundamental elements of nature must be connected to them. So they connected fire with tetrahedron, air with octahedron, earth on hexahedron, and water on icosahedron. Those were the 4 fundamental elements they believed to exist, and based on these they said that there must be a 5th element called quintessence. Okay, so that was an attempt by Greek philosophers. So you see, the to describe nature through symmetry was an attempt that is quite old, but now we know that this does not make sense. But the philosophy remains, and we'll see that the same thing came back in modern days in a different setup. So then I can say that symmetry is simplicity, and symmetry gives you extreme predictive power. Okay, if you do not have symmetry, life is very hard. Like, for example, you have this half of a butterfly, and you can paint just half of it, and then you can make the other half just by what? Making a chap. You call it chap in Bangla, right? You just need to know half of the butterfly to know what the full butterfly looks like. And you see, also drawing a circle is extremely easy. You just need to know the center and the radius, all that, right? You can draw the whole circle just by these 2 pieces of information, whereas the circle is a set of infinitely many points, right? Now look at this slice of pizza. That's just a tiny part of a pizza, but you can more or less guess what the pizza looks like just from symmetry, right? These are symmetry of objects that we see. But I'm gonna give you the last example. That's an example of symmetry in the laws of physics. For you, I wrote down the gravitational law of Newton, and perhaps you never thought about this law, that this is an extremely powerful law, because Newton found this law like 300 400 years ago, and this law is still valid, right? This law did not change. So the laws of physics do not change over time. And Newton discovered this law in England, and this law also holds in Bangladesh or in USA or in Mon. Everywhere the laws of physics don't change when you move from one place to another. And also this law is rotationally symmetric, right? No matter where the earth is from sun, as long as the distance is the same, no matter which angle it is, the force is going to be the same. Think about this. If the force did depend on angle, the gravitational constant g would be a function of the angle, right? And it would be a big mess. Symmetry makes physics extremely simple and predictive, and this symmetry does not exist in some other fields like economics or say social science. That's why trying to predict an economic meltdown or the onset of a pandemic is a very hard problem. In physics, we can say when a comet is going to come in 200 years. Physics is extremely powerful because of symmetry. Okay. Okay. Now that's all with the philosophical part. I think I could convince you that why symmetry is good. And now I will go into physics. And any questions so far? By the way, if you have a question, please feel free to ask and stop me. I would appreciate that. Any questions so far? Okay, I move on then. So
Sir,
I would like to, yes. Do
can
you
you
have a
upload the
question?
slides beforehand?
Yes.
No, like, can you upload the slides in chat or somewhere?
Upload the slides. Yes,
Yeah,
of course.
that would be.
After the talk, right?
Okay.
I don't know how to do it right now.
Oh, okay. That's good. Okay.
Do you not
Thanks.
see the slides
No,
in
it's like
Zoom?
if I want to go back somewhere, if I want to go
I
back and
see.
see something, that's right.
Kamrul sir has my slides, so I think he can do it. Thank you. Yeah. Okay. So
Sir,
implications of symmetry. If you have symmetry, what does it mean? So in the next few slides, I will show you that symmetry of an of an equation means that you have many solutions to it, and the symmetry transformation will map one solution to another. Through some examples, this will be clear to you what I mean. Okay. So take example one, the cubic roots of unity. Okay, so you have this algebraic equation z cube equal to 1, and we all know that this has three solutions. Those are complex numbers. You have this xi naught, which is 1, xi 1, which is this complex number, which is on complex plane. You have this green line, and xi 2 is this blue line, right? So you have these three roots of unity, and these roots, when you draw them on the complex plane, as you see that there is a symmetry, right? This symmetry we call a Z3 symmetry. If you rotate it by 120 degree, it looks the same, right? And this Z3 symmetry is also a discrete symmetry, because there is no infinitesimal version of this. If you change this, if you rotate this by a small angle, say, then it does not look the same, right? So it's a discrete symmetry. That means to make the symmetry realizable, you need to make a finite change. So the symmetry is this. As I said, you send z to z prime, which is a 120-degree rotation in the complex plane, z prime, which is z times e to the power twice I pi by 3. And since e to the power twice I pi is 1, as you see that if z cube is 1, you also get that z prime cube is 1 as well. So that's a symmetry. You made some change, you send z to z prime, still the equation for z and the equation for z prime are the same. You call it a symmetry. But now let's solve this system, and you have the solutions, and you know that the solution will be mapped, right? Because if you make a 120-degree rotation of z of xi naught will map to xi 1, and xi 1 will map to xi 2, and xi 2 will map to xi naught, so on and so forth. So the solutions, they change, but from one solution you get another solution. That's my point. Now I come to a physics example. Example 2, you all know this. It's a harmonic oscillator in one dimension, and you have this differential equation with omega being the angular frequency. Okay, and you all know that the solution is this. But did you ever think that why in my solutions there are two parameters, a and phi? What do they mean? Actually, they say that you have infinitely many solutions, because a is a real number and that can take infinitely many values, and phi is also a real number that can take infinitely many values. So you have infinitely many solutions. But why? Because of symmetry. There are actually two continuous symmetries here. Look, if I make a time transformation, namely if I send t to t prime, which is a constant shift in time by t naught, the equation will not change its form, right? The form will be d squared x by dt prime squared. So you just replace t by t prime, but the form does not change. So that's a symmetry. But when you make this transformation, the solution will be mapped to something else. In particular, the phase will be changed, because if you solve for x but want to write the right hand side in terms of t prime, you see that to make it omega t prime, you need to make the angle phi as phi prime, which is given by this. So you have a solution that of the same form with a different phase. So since there is a symmetry, because of symmetry, you have very many values of different phases, because you can shift your time as much as you like. Now then comes this question of scaling transformation. Look, in this original equation, if you replace x by x prime, which is lambda times x, where lambda is a non-zero real number, positive say, then this equation does not change, because you can multiply the both sides of this original original equation by lambda, and then you see that you will have the same equation in terms of x prime, right? So that's a symmetry. We call it a scaling symmetry. But that symmetry will map one amplitude to another, because if you send x to lambda x, you will have to send a to lambda a, right? And that is precisely why you have infinitely many possible values of the amplitude, because of the scaling transformation symmetry of the equation. Then comes a more complicated example. You must have learned it if you have taken classical electrodynamics course. Is the electromagnetic wave equation. So you have this Laplacian operator here, and then you have this 1 over c squared d squared dt squared, where c is the speed of light and E is the electric field that describes part of the electromagnetic wave. But see, I will show you that this particular equation has many symmetries. But for now, let's look at one of them, which is scaling again, but of all time and space. So t, x, y, z goes to t prime, x prime, y prime, z prime, which we call lambda t, lambda x, lambda y, lambda z. You see that this must be a symmetry, because if lambda is non-zero, you just need to divide both sides by lambda squared, and then you have the same form of the equation, just x, y, z, t replaced by x prime, y prime, z prime, t prime. The form of the equation does not change. So it's a symmetry. But now look at the solution. So in particular, you have the plane wave solution here. You can write the plane wave solution in this form, where omega is the angular frequency, E naught is the amplitude, and k hat is the unit vector in the direction of the wave propagation, and r is the position vector. If you want to write this solution in terms of the primed variable x prime, y prime, z prime, t prime, you see that it looks like this. So it means that when you make this transformation, you have the same form of solution, but now your frequency is factored by a factor lambda, 1 over lambda to be precise. So the frequency will be different in this rescaled coordinates, right? So this gives you an answer of why electromagnetic wave of any frequency should exist, because there is a scaling symmetry of simultaneous scaling transformation of space and time. Okay, just because of this simple fact, electromagnetic waves should exist for all wavelengths. Okay, so there is a teaser for you. I would like one of you at least to give an answer to my following question. When you look at the ferromagnetic domains of a piece of ferromagnet, you see all the domains have different direction of ferromagnetic alignment. And why is that the case?
Why is that the case? Because symmetry is
Yes.
broken.
Symmetry is broken by a solution, of course, right? When
Hmm.
you have a particular solution, say you take z cube is 1 and you look at a particular solution, that particular solution always breaks the symmetry, because when you make a transformation on the solution, the solution does not come back to itself, right?
Hmm.
So you take a particular ferromagnetic domain, it has a direction of alignment, but then if you take a different ferromagnetic domain, it has a different direction of alignment. Why is that the case? I,
See,
I want some of you to give an answer to it. Is there any answer?
frequency.
Well, it's I give you a hint. Is it has to do with rotational symmetry?
Hmm.
Any answer?
Without any external agency, they should point in any possible direction, randomly oriented.
No, the ferromagnetic domains, in a domain, all the fundamental dipoles are aligned in a particular direction. But why there are different domains of different alignment, like here? You know that that's the case, right? So the fact is that the interactions of the magnetic dipoles is rotationally invariant. Okay, there is a symmetry, rotational symmetry, but a particular solution, namely a particular domain, will not have the symmetry. When you make a symmetry transformation, you get a different domain of different alignment, right? And so all these different domains actually represent all the different solutions that the system can have. Okay, because when you make a rotation transformation in a given domain, you get a different domain, and that different domain should exist as well, and it does. If you take a big piece of ferromagnet, you will find different domains pointing in different direction, and if you take an average, you will see that there is a symmetry statistically, right? So the symmetry is manifest in this sense, but a particular solution will kill 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 this symmetry. Just like here, that the symmetry is manifest when you look at all the solutions of cubic root of 1, right? If you look at one solution, it does not have the symmetry. By a 120-degree rotation, you get one solution from another. So the answer is there, that all possible direction of ferromagnetic alignment exists because of inherent rotational symmetry of the problem. That's rotation in space. Okay, now I will talk about global symmetries. By now I gave you some examples, but let's be more precise about it. Global symmetries of the laws of physics. First one
Excuse
is,
me, can I ask a question?
yes, sure.
Okay, the previous question can relate something about the axis. Like the
Sorry?
axes are different and the axes are moving. Some axes are moving and some axes are not moving. The rest of others. So there is the difference I'm making. Is there something?
Sorry, I did not understand you. What was the point?
My
Can you
point
explain a
was
bit?
that Yes. My point was that if we consider these directions about into different particular axis, then if the axis is not similar to another axis, so the situation can be created. So is this worth it or not?
No.
I'm just saying that if you take an arrow, right, and you rotate the arrow will point in a different direction, right?
Yeah, right.
So if you have rotational symmetry, you would have different arrows pointing in all different directions. But one single arrow will break the rotational symmetry, right? Because if you
Okay.
rotate that arrow, it points in a different direction, and then it's a different configuration. So you have all solutions of the given problem, and all solutions, they show up in a ferromagnet, right? If all solutions don't show up in a ferromagnet, you will find that solution in some other piece of ferromagnet, right? that's
Okay. Got it.
that's the point. Okay,
Okay. Thank you.
welcome. So let's talk about translation in space and time. I already explained you in the context of Newton's
Okay.
gravitational law that, yes,
Can I ask another question?
sure.
Is there, could you say that there is certain number of solutions to a equation that we could say that it will not break that equation's symmetry? Is there a minimum number of solutions to a given equation?
I would say that you need to have at least two solutions to have a symmetry, right? For example, the minimum number of symmetry I can think of is Z2, which is reflection, x going to minus x, right? If you want to solve for x squared equal to 1, that x going to minus x is a symmetry in complex plane, that's a rotation by 120 degree. And yes, I don't think with less than two solutions you can have a symmetry. But in physics, typically you have infinitely many solutions, because the symmetries are not discrete, they are continuous symmetry.
Yeah.
And continuous symmetry, of course, will give rise to infinitely many solutions. Does that answer your question?
Yeah. Is there any counter example of that there is no infinite amount of solutions, but it's symmetric?
What do you mean by symmetry? I don't know. I am talking about symmetry of an equation. This could be an algebraic equation, this could be a differential equation, but in all cases you have a solution of the equation, right? If you don't have a solution of an equation, what's the point of having the equation?
No, I am just asking that is there any counter example of that there is no infinite amount of solutions, but a certain amount of solutions, but it's symmetric?
I already told you, right? This is one example. This z cube equal to 1 has 3 solutions,
Okay,
right?
okay. Thank you.
And there are 3 solutions. And even with two solutions, z squared is 1, has a symmetry.
Okay, thank you.
It's called z2. In this case, it's called
Yeah.
z3.
Yeah, that's my answer. Okay, thank you.
Okay. Now let's talk about translation in space and time. So you can shift time by a constant t naught and x, y, z by constant x naught, y naught, z naught. And let's take once again the electromagnetic wave equation. And if you take that electromagnetic wave equation here I wrote, you see it does not change the form by a translation in space and time, because x just goes to x prime, y goes to y prime, z goes to z prime, so on and so forth. Because if you make a constant shift, as you see that the differential operators don't change, right? Because it's a constant change. Okay, so it has the same form, and you see you have 4 continuous symmetries. Why continuous? Because you can make these constants t naught, x naught, y naught, z naught to be infinitesimally small. They don't have to be finite. So that's what you mean by a continuous symmetry. So you have 4 continuous symmetries here, and because of this translational symmetry, you have infinitely many solutions. And guess what? You have a phase, right? They will change the phase. And why the electromagnetic wave, if you solve for a plane wave solution, that will have a phase, and the phase can take infinitely many values. This is precisely because of this translational symmetry, as you might have guessed from the example of harmonic oscillator. So what it means that if you perform an experiment in physics, it holds good in all places, in Dhaka, in Antarctica, on moon, in Andromeda galaxy, wherever, and it holds good at all time. Yesterday, today, tomorrow, 100 years from now, and 2000 years ago, so on, so forth. That's what makes the laws of physics so powerful. You don't need to change, you don't need to come up with a new law every day or everywhere. So then there is also a symmetry of rotation of space. I give you one example where you rotate with respect to the z axis that you choose, but you can also rotate with respect to x or y axis. So it looks like this transformation. And in this case, you have 3 continuous symmetries because the angles of rotation can be as small as you like. And these continuous symmetries, they don't change the wave equation. X just goes to x prime, y prime, z prime. This is because the wave equation has this Laplacian operator dx squared, well, dy squared dz squared, and it is invariant. It does not change under a rotation in space. So it takes the same form, and that's a symmetry. And because of rotational symmetry, what happens? You see light wave going in all direction, right? Light waves comes to you in all direction, no problem. Why? It comes precisely because those all infinitely many directions of motion of light can exist because of rotational symmetry. Okay, because the problem is rotationally symmetric. I give you an example in the context of electromagnetic wave, but in general, that's a symmetry of fundamental physics. It means that if you rotate the frame of your lab by an angle, your experimental outcome will not change. Okay. Okay. Then there is another symmetry that we learned like 100 years ago, 115 years ago to be precise. That's motion with uniform velocity. This symmetry was known since the time of Galileo, but the form was known for small velocity, where the velocity is small compared to the speed of light. So it means that if you are doing an experiment with an apparatus and you move with respect to the apparatus with a constant velocity, you will see the same laws of physics. And if you don't move, you find the same law. Same law means that the form of the equation describing the physical phenomenon will look the same. So this transformation, as you see, that we know now of relativity, that when you move by a constant velocity, no matter how fast you go, the speed of light is the same in vacuum, right? To take this into account, you need to make this transformation a bit complicated. So I made this transformation in accordance with Einstein, and these are the transformation that makes sure that if you move, the speed of light does not change. And these are called Lorentz transformation or Lorentz boost. Okay. So why there is a transformation of time, this is because you are moving with a finite velocity while the speed of light does not change. So if you change x, you also need to change t. If you don't change t, there is no way that you can have a constant speed of light. Okay, so that is as simple as that. So time cannot be an absolute measure if you want to keep the speed of light fixed with respect to uniform motion. Okay, so these are three continuous symmetries because your velocity can be infinitesimally small, right? It can be zero infinitesimal small, or it can go up to the speed of light. Beyond that, it does not make sense. Okay, but another thing I wanted to point out here, that these transformations also mix electric and magnetic fields. There is no way actually to make a distinction between electric and magnetic field. It's like the same part of the two different parts of the same thing, like the head of an elephant and the back hind part of an elephant, right? So if you move, you have a charge, right? You have a fixed charge, and from that charge you have a electric field, but no magnetic field. But now if you move with respect to the charge with a constant velocity, the charge will move with respect to you, and you know that the moving charge creates magnetic field. So motion with uniform velocity mixes electric and magnetic field. So to see that the electromagnetic wave equations have this symmetry, you need to write both electric and magnetic wave equations. So the form you can prove that could be an exercise for you, that this differential operator here that I wrote does not change its form by this transformation. Okay, it's just x, y, z and t goes to their primed counterpart, but its form is the same. Whereas the electric and magnetic field, they mix with each other with a linear combination, but since the original equation had zero on the right hand side, so the linear combination, if you take, I mean, the form will not change. Basically electric and magnetic field are vectors, and they might mix into each other. And you can also see that the Lorentz transformation, because of Lorentz transformation symmetry, you have many different amplitudes of the electromagnetic waves. Some waves could be very light. When you say that the signal in your cell phone is weak, it means that the amplitude is small. When the signal is good in your cell phone, the amplitude of the wave is big. So the amplitude also changes. You have many different possible, infinitely many different possible values of the amplitude because of this Lorentz transformation symmetry. Okay, now I will also talk about some discrete symmetries in fundamental physics, like mirror reflection P or parity, where x, y, z goes to x prime, y prime, z prime, and you just flip their sign. X goes to minus x, y goes to minus y, z goes to minus z. This is mirror reflection. This is a discrete symmetry, right? Because there is no infinitesimal version of that. But you also see in this case the wave equation, the electromagnetic wave equation does not change its form, because if you move x to minus x, dx does not change. Dx changes by a sign, but dx squared does not change. Whereas the magnetic field B actually is called a pseudo vector. It changes sign under a mirror reflection, but the electric field does not. If something changes sign under mirror reflection, we call it a pseudo quantity. Like in this case, the magnetic field is a pseudo vector, but the electric field is not a pseudo vector, so it does not change. In any case, the form of the electromagnetic wave equation does not change. So parity or mirror reflection is asymmetry of this electromagnetic wave equation. That's why if you look at a light wave in a mirror, that will look like a perfectly okay light wave to you, because of that light wave can actually exist in reality. The point is that whatever you see in mirror can also happen in real life. That's the meaning of mirror reflection symmetry. Okay. And yes, so mirror reflection makes no difference in an experiment. If you do an experiment and you have the result, if you don't look at the apparatus directly, but you look at the mirror reflection of the experiment, you would find the same laws of physics. That's what you mean by parity symmetry. But now we know more, for almost 70 years, 64 years probably, yes, that the mirror reflection symmetry is actually broken in nature. That's broken by uh, weak weak interaction in radioactive beta decay. You see that this symmetry is broken. Namely, if you look at the radioactive beta decay and you look at its mirror reflection, you immediately know which one is a mirror reflection and which one is reality. It's like if you have left-handed screw and right-handed screw. If you take a mirror reflection of a left-handed screw, this will look like a right-handed screw, and vice versa. Now if you know that you only have right-handed screws and you do not have any left-handed screws, now if you make a mirror reflection, you immediately know that if you are looking at a mirror reflection of something or if you are looking at an original thing. So in weak interactions also, the players there are the leptons, for example, the in particular the electron. This has two components. One is right-handed, one is left-handed. One is the mirror reflection of another, and they combine to make the electron. But these parts, they don't talk the same way to the weak interaction, namely the W and Z particles that mediate the weak force. They do not talk the same way, but they talk the same way with light. That's why these electromagnetic phenomena are parity symmetric. Mirror reflection is fine, but it's broken at a more fundamental level. So if someday somebody from a distant planet calls you and asks you what is the what is left and what is right, you can explain to that alien that do this particular experiment with radioactive beta decay, and that's how you know what is left, what is right. Okay. Then there comes this charge conjugation symmetry. This is a symmetry of exchanging particles with anti-particles. If you take electron, for example, you find some laws of physics. If you take an anti-electron, you should find the same laws of physics. In particular, say if you make a hydrogen atom with an electron and a proton, it has some energy levels, right? And it should have the same energy levels if you make an anti-hydrogen atom with an anti-proton and an anti-electron. So that's charge conjugation symmetry means. Okay, now this charge conjugation symmetry has to do with anti-particles, and these anti-particles also show up when you think in terms of symmetry. Namely, you take quantum principle, the laws of that was found by Schrodinger, Heisenberg, and others, and you say that I want to make it invariant under or covariant under Lorentz symmetry. So if you want to marry Lorentz symmetry with quantum principle, you immediately realize there should be anti-particle corresponding to each particle. Since there is wave particle duality in quantum principle, electromagnetic wave has its corresponding particle that we call a photon, but photon is its own anti-particle. It's not a different particle. Anti-photon and photon, they're the same thing. And that is also why the electromagnetic wave equation is trivially invariant under charge conjugation, because it has to deal with electromagnetic wave of photon and its own anti-particle. So nothing changes there. So C is a symmetry also of pure electromagnetism. But this charge conjugation symmetry is once again broken by the same phenomenon as I said. So that weak in interactions, in that beta decay, you violate parity, you violate charge conjugation as well, such that when you make both transformation combined, they're a good symmetries. Namely, simultaneously you make a parity transformation and charge conjugation, and then this will be a symmetry. Okay, I will tell you why that's the case. Last but not the least, we have this discrete symmetry of time reversal. Namely, t goes to t prime, which is minus t. You flip the direction of time, and you might ask, how can you go back in time? Well, I cannot go and you cannot go as well, but for sure elementary particles can go both forward and backward in time. For elementary particles, the arrow of time does not exist. Okay, and actually a particle going to the past looks the same as an anti-particle going to the future, and vice versa. And our electromagnetic wave equation is also symmetric under the time reversal, because if t goes to minus t, nothing will change since you have dt squared there, right? So this is a symmetry of electromagnetism as well. But this symmetry, time reversal symmetry of fundamental particles, is also broken in some other phenomenon called decay of neutral cone. There are more phenomenon that breaks time reversal, but this was the one that was observed first. Okay, but I told you of these three symmetries, P, C, and T. Combined, CPT is always a symmetry. Namely, if you make a transformation, you change, you make a mirror reflection, you replace particles by antiparticles and vice versa, and you change the direction of time. Combined, you will always have a symmetry. That's a theorem that's called the CPT theorem, and CPT is always combined, so always conserved. So far we did not see any event in physics that breaks CPT. If CPT is violated, this symmetry is broken by some phenomenon, it means that particles and anti-particles will not have the same mass. But so far we have not seen this violation, and there are good theoretical reasons for it. Okay, any questions so far?
Can I ask a question? Except
sure.
the equation. Okay, that what you have told, the time reversal. Okay, so is it any connection with the parallel universe? Because we know that in parallel universe time is running on anticlockwise, and if look on a black hole sucks everything inside us. But in the parallel universe, it shows
we are talking about one single universe.
only
Look,
one single universe.
if you look at relativity, you immediately realize that space and time are on the same footing, right? You mix them
Yeah.
when you make a Lorentz transformation. So from perspective of special relativity, time and space, they're on the same footing. So if you can go forward and backward in space, why cannot you go forward and backward in time? It turns out that macroscopic objects cannot, but microscopic objects can. Okay, so that's some emergent phenomenon called entropy. Because of that, because entropy will always increase, and the fact that we cannot go back in time is connected to it. And for fundamental particles, the notion of entropy as such does not exist, because you need a collection of particles to make the notion, right? So yes, so I am not talking about any parallel universe or whatever, but I would like to hear more questions from someone else, for example. So far I have gone through some slides, and it would be nice to hear some questions.
Can I ask you a question?
Yes, sure.
As you have said that photon is an antiparticle of itself. Is it because photon has no charge?
That is right. You need to have some sort of thing to see some charge or some label, right, to distinguish a particle from an antiparticle. And charge is the only way, because they have the same mass. They also should have the same spin. Apart from spin and charge, the only they must be the same for both particle and antiparticle. And if it does not have a charge, you cannot distinguish. Yeah.
Sir, I have a question. Can I go for it?
Yes, but one more thing. You have neutrino that also does not have electric charge, but neutrino and antineutrino are not the same. This is because although neutrino does not have electric charge, this has some other charge. It has charge under weak gauge field. So yes, please.
Sir, does the mechanics
Yes.
of black holes maintain time reversal symmetry?
Ooh,
I
can
mean, if I forward time or backward time, I mean the change of entropy will be always the same.
Can I postpone these questions for the last part of my talk, because these are more advanced things. At this level, I would like to be more down to earth. The short answer is complicated, because black hole is a macroscopic object, right? It's not a microscopic thing. And but yet gravity plays role there. So far what I am telling you is mostly for a theory where gravity does not exist. If gravity exists, things get more complicated. Okay, so I will postpone that for last part of my talk.
Okay, sir. Sir, I have another question
Yes.
about Lorentz transformation
Yes.
and related to the mass. Sir,
Yes.
what do you think about the Lorentz transformation of mass? Because Einstein
Well, there
have
is nothing called Lorentz transformation of mass. All we have is the Lorentz transformation of momentum. Okay, momentum transforms under Lorentz transformation. That's all. Now, some people tend to say that the definition of momentum is mass times velocity. Well, that's not true. The definition of momentum is mass times velocity in the Newtonian world. That's a Newtonian notion. Okay, momentum is something whose rate of change gives you the force. That's all. Okay, so if you insist that mass times velocity is my definition of momentum, then you get this weird nonsensical results like the Lorentz transformation of mass, but there is just one mass. Yes, mass does not Lorentz transform, but momentum does. Yes.
Yes, sir. I also think that this term is alleged, but in our textbook it is written that some
Those are wrong because back in the early days of relativity, people did not understand the theory well. It takes many years to understand a theory, right? Unfortunately, we follow old textbook. Somebody makes a copy from an old textbook, and then the mistake goes on and on. If you take a good modern book of relativity, you will see that it does not talk about relativistic mass. There is just one mass that does not change. Okay.
sir, then I got from the Feynman lecture, and he also deprived the formula for relativistic mass, and I then got a little bit disappointed. And what
Well,
to
during Feynman lived 50 years ago, right? I told you things, it takes time to clarify things, right? Right. Just because Feynman said something does not mean it has to be true. Okay. So I would like to move on to something called phase rotation.
okay, sir,
So
thank you.
now you're welcome. Now we'll talk about more complicated symmetries. Suppose we have a complex field. What is a field? A field is, say, a function of space-time. You have a function phi that depends on x, y, z, and t, and you make a change. Phi goes to phi prime, such that you have this function phi multiplied by e to the I alpha, where alpha is a constant. Okay. For sure, this phase rotation does not change the norm, right? Because if you take the norm, the phase factor will cancel out and you get back the same thing. And in quantum mechanics, not changing the norm is important, because this phi might describe a wave function or a field. So, okay, this transformation does not change the norm, but take, for example, the wave equation of this complex field phi, which looks like this, is the same wave equation as the electric and magnetic field, but now we don't have a real field like E or B, we have a complex field phi. Okay, now this make this phase rotation, and you see that the form of this equation does not change, because this phase factor is a non-zero factor, and of course you can multiply both sides of this equation by this phase factor, and the form does not change. You just replace phi by phi prime, but it's the same form of equation. So this phase rotation is a symmetry of this complex field, of this wave equation of the complex field. But as you see, it's a mathematical symmetry, right? Because you are describing the same physics, because at the end of the day you need to compute the wave function squared, that does not care about this symmetry. For example, this phase, right? This phase is gone. So you have infinitely many equivalent mathematical descriptions of the same physics. So it's a mathematical symmetry, but it has physical consequences, as we will see soon. Okay. So now another teaser for you. Why does this picture not look odd to you? Why you think that this picture is okay?
Because human face is symmetric, mirror symmetric, that is.
But you don't see the face of the girl, right? Do you see the face of the girl?
No.
You don't, right?
No.
So why does it look normal to you?
Because the picture of the face that I see is a very possible configuration of a face, because human face is mirror symmetric.
It's
That's
not
right.
only the face, it's also the hand.
the hand is, I don't think the hand is important, but the face
Is
is
the
mirror
face.
symmetric.
You are
So
right.
yeah,
So human face is approximately bilateral symmetric or mirror symmetric, although this is not quite symmetrical because the girl has some sort of red spot underneath the corner of her eye, and but still it is approximately mirror symmetric. So when you make a mirror reflection, left goes to right, right goes to left, it's not the same face, but it is approximately the same face, and you approximately see the person that you would see, and it's a perfectly all right person. It's not an unusual face because of the mirror symmetry in our face and the fact that mirror transforms left to right. Yes, that is the answer. Okay, any other questions at this point? If not, I will move on to the next topic. Yeah. Okay, so it's time to move on to Noether's theorem, implications of symmetry, conservation laws. Okay, so there is something called Noether's theorem. Noether was a physicist who came up with this theorem, and I show you her photo in the very beginning of my talk. So the theorem mainly says it's a mathematical theorem that we teach in quantum field theory 1 course. So I'm not gonna go into the mathematical detail of it, but it says if you have a continuous global symmetry, by now you know what is continuous symmetry, that there is an infinitesimal version of the symmetry. You also secretly know what a global symmetry is. Global symmetry means where the symmetry transformation parameter, the change that you are making is the same at every point in space and time. For example, this phase alpha is not a function of x, y, z, and t. Like here, say if you have this Lorentz transformation, this v is the same in all points in space and time. Or here the angle theta does not depend on x, y, and z. Or here the t naught, x naught, y naught, z naught does not depend on what the value of t, x, y, and z are, right? So these are called global transformation. You make a transformation by a constant that does not depend on where you are, right? So these are global transformations. So if you have a continuous global symmetry of a system, you have a conservation law. So I do not go more into the technicality of the theorem, but in short, this theorem, the converse of this theorem does not have to be true. That if you have a conservation law of some quantity, it does not necessarily mean that you always have a continuous global symmetry for it. Anyways, so examples of Noether's theorem that we teach in field theory courses is translation in space, and you can prove that it gives the conservation of linear momentum. We have learned that momentum is conserved, but only when you are at the advanced stage of physics learning do you realize that this momentum conservation has a deeper reason to be true. It's because physics does not depend on where you are. If your physical laws hold in every place uh, every place you can go, you will have conservation of linear momentum. Likewise, if the laws do not change with time, if the laws are valid yesterday, today, tomorrow, you will have conservation of energy. If your laws do not change when you rotate your frame, you have conservation of angular momentum. Okay, if you have symmetry of Lorentz boost, namely if you are moving with a uniform velocity and your laws do not change, you have also conservation of position of center of mass, and it does not change actually by a uniform motion. And last but not the least, I showed you the phase rotation. I said that the phase rotation is a mathematical symmetry, but it has a physical consequence. Namely, because of this phase rotation symmetry, you have conservation of electric charge. And Noether's theorem does not tell you to, in order to have a conservation law, the continuous symmetry that gives rise to a particular conservation law does not need to be a real symmetry, real in the sense that it could be a purely mathematical construct like the phase rotation, but still the theorem holds. The theorem does not care if the symmetry is a purely mathematical construct or not. Okay, now I give you directly a teaser. So we all know about the Kepler's second law, right? Kepler's laws of planetary motion. The second law says that a planet sweeps equal area in equal time. I would like to know from one of you why this is true.
Because of conservation of angular momentum.
Who are you?
I'm Partha Sarkar.
Okay, so because of conservation of angular momentum, can you say more? What does the angular momentum have to do with the area?
So if you look at the equation of dA over dt, which is the area traversed in unit time, you get that it's equal to, after you do some mathematics, it's equal to L over twice m, where L is the angular momentum. So
I think you are right, but there is a simpler answer to it. Basically, angular momentum is v cross r or r cross v.
yeah. So it's a central force.
But this is precisely the area swept in unit time. V cross r is simply the area you sweep in a unit time. And I wanted to know more from you. It is because the Newton's law is rotationally invariant. It has a rotational symmetry. And because of rotation, as I showed you towards the very beginning, right? That this law does not care about the angle, right? So because it is rotationally invariant, there is conservation of angular momentum, and angular momentum is precisely up to a factor 2 or half is precisely the area the planet sweeps out in unit time. So for sure this Kepler's second law is actually conservation law. Okay, it's the conservation of angular momentum up to a factor, and this happens because Newton's law of gravity is rotationally symmetric. Okay, so then I move on to a more interesting topic of symmetry breaking and Nambu Goldstone mode. Before that, I would like to hear some more questions if you have.
I wanted to ask a question in the parity breaking part.
Yes.
So my question is, how do you experimentally observe a mirror event? I mean, there's a instance given there that the mirror symmetry was broken, but how do you deduce that a mirror event has happened?
Well, as I said, there are right-handed electrons and left-handed electrons, right? Certain handedness of electron talk to the weak in interaction, certain do not, right? So there is a asymmetry of left and right when it comes to the weak in interaction. Okay, if something is not left right symmetric, then of course the mirror symmetry will, the mirror image will look different, right? So just by looking at at the mirror image, for example, if you have a beauty spot on your right side, now you know if you are looking at your mirror image or not, right? So it's just that. So the laws of weak interactions, they are not reflect mirror reflection symmetric. It comes when you make a mirror reflection, it looks like something that does not actually happen in reality. Okay, yes, that's how you know.
Okay, thank you.
Welcome. So now comes a very interesting topic, symmetry breaking and Nambu Goldstone modes. Basically, so I will give you the idea first of spontaneous symmetry breaking. So if the ground state of a system, ground state means that the configuration of minimum energy configuration of a system, it might not respect the symmetry of the system, right? Like I said, the solution of a problem that does not usually respect the symmetry. So ground state is a solution of, of the system, is a solution of the equation that describes the system, and it does not have to respect the symmetry, right? If that's the case, we say that the symmetry is spontaneously broken. Okay, so if you have such thing, one example is as I already said, that the ferromagnetic domain, it breaks the 3D rotation symmetry. When you write down the Hamiltonian or Lagrangian or the equations describing the interactions of ferromagnetic dipoles, you see that those equation Lagrangian or Hamiltonian is perfectly rotationally symmetric. So there is a inherent symmetry of the problem. But as soon as you have a ferromagnetic domain, that domain, all the tiny dipoles, they align in the same direction. So the rotational symmetry is broken by the ground state, namely a particular domain. But the rotational symmetry is not completely broken, because in the original theory you have a three-dimensional rotation, now you have a two-dimensional rotation, right? Because if you point in one direction, you still have the axial symmetry, right? Namely, you can make a rotation by choosing an axis that's the same as the direction of the arrow, then things are symmetric as well. So actually 3D spatial rotation breaks down to two-dimensional spatial rotation. So how many symmetries are broken down by the spontaneous breaking? Do you know? Originally in three-dimensional rotation, you can make a rotation in three different ways, right? With respect to x-axis, y-axis, z-axis. Now you can make a rotation with respect to just one axis. So how many symmetries are broken here?
Two.
Two, right? So yes. So you have two symmetries that are spontaneously broken. It's broken by the ground state. Now what happens is that in ferromagnetic material, there exists something called spin waves or magnons. But what are they? They are actually that the individual magnetic moments can undergo precision like this that you see in this picture, right? They can make a precision in a left-handed way or a right-handed way. So there are two modes of excitation, right? These are called spin waves, and their quanta are called magnons, and their gapless excitation. Gapless means you can have this excitation with infinitesimally small amount of energy. You don't need a finite finite amount of energy to start this, right? This can happen even for an infinitesimally small amount of energy, and those are called gapless excitations. Okay, so you have two broken symmetries and you have two gapless excitation, because the thing can make a precision in a left-handed fashion and in a right-handed fashion. Okay, this is basically the Nambu Goldstone mode, and this is also an example of the Goldstone theorem, that whenever you have a spontaneous breaking of a symmetry, namely the ground state does not respect the original symmetry of the problem, you have gapless modes, and the number of gapless modes is the same as the number of broken symmetries. So Magnon is one example, but I will give you more examples. But to summarize, the Goldstone theorem says if you have a continuous global symmetry that is spontaneously broken, by this strike through, I mean that the symmetry is spontaneously broken, you will have gapless mode, and number of broken symmetry, as I said, is also the number of gapless excitations. So when you are dealing in the context of relativistic theory, you call it a Nambu Goldstone boson in the relativistic theory. But the symmetry, the continuous global symmetry that you might be dealing with might be almost exact symmetry, namely the symmetry is almost a symmetry, like the symmetry of a human face, right? It's not a perfect symmetry, but almost perfect. So if you have an almost exact symmetry which is spontaneously broken, then you have an almost gapless mode, or an almost massless particle. So these will be called the pseudo Nambu Goldstone mode or pseudo Nambu Goldstone boson. I will give you one example of this right now. So examples of Nambu Goldstone mode. All these things are known to you, but now I will give you a different perspective of something that you know. Can I have a break, please? Just a second.
Yes.
Sorry. Yes. So we all know that if you have a string, and the string can vibrate in two direction, right? If you have a string like that, you can have an oscillation like this or like this. This is because the presence of the string, it breaks translational invariance, right? If you move in a transverse direction, you will hit the string at some point, just because the string itself exists. The very existence of the string breaks translational invariance in two direction, namely direction that are perpendicular to the string. Since this presence of the string, you might think of it as a ground state configuration of some theory, and that is precisely because why the string can vibrate in two different modes. And if the string is infinitely long, you also have symmetry along the string, and you can have gapless modes, namely you can produce a wave of an arbitrarily large wavelength which has very small amount of energy. Likewise, if you have a pond, if you are jumping down on a pond, right, you have air and suddenly you have water. So just because you have water, it breaks translational invariance, right? It breaks at the surface. Inside water, you once again have translational invariant, because fluids look the same everywhere. But the surface breaks it, and you have breaking of one translational invariance, namely perpendicular to the pond, and that is precisely why you have waves on water surface. Okay, ripples, right? So, and yeah, that's an example of a Nambu Goldstone mode. Now, sound waves in fluids, you have when you have a fluid, the very existence of the fluid will break Lorentz boost transformation, because if you run inside a fluid, you will feel, right, that there is a fluid. In vacuum, if you run, you don't feel anything. So uniform motions you will feel when you are in a fluid, or a non relativistic version of that is the Galilean symmetry, and the Galilean symmetry is broken when you uh, have a fluid. The very existence of the fluid breaks it. The Lorentz invariant, or in non-relativistic version, the Galilean invariance, and that is why you have sound waves in fluids, and sound waves can go in three direction, because you have the bulk of the fluid. The sound wave can go in the x-axis, y-axis, z-axis. So it's three different modes of vibration, and because you have three different symmetries, continuous global symmetries are broken. And I already gave you the example of ferromagnetic spin wave. This is because of the spontaneous breaking of the rotational symmetry. And last but not the least, there is this chiral symmetry, the left and right quarks. Quark is another fundamental particle like electron, and they also come in right-handed and left-handed uh, mm, forms, quarks. And quarks can the symmetry between the right-handed and left-handed quark is called chiral symmetry, and this chiral symmetry is almost exact. This is because whenever you have a mass, the mass will break the symmetry between left and right. Since quarks have mass, so for sure this symmetry is not exact, but these up and down quarks have small mass. So small mass means that the symmetry is almost exact. So, and this symmetry is spontaneously broken by the QCD phase transition of the early universe. So you have a spontaneous breaking of an almost exact symmetry. So you should have mm, almost massless particle, and that is precisely why pions, as we know, the some hadrons, they are very light compared to other hadrons like neutrons, protons is like 935 MeV, whereas the pion is like 130 MeV, something like that. They're much lighter than any other hadron, and that is precisely the reason that pions are the pseudo Nambu Goldstone boson of spontaneous breaking of chiral symmetry. So now there is a teaser for you. So vibrational modes in a solid. So how many vibrational modes should exist in a solid? Hello? Hello?
No, I think three, because if it's a three-dimensional solid object, then three different modes.
Well, how many symmetries are spontaneously broken by the existence of a crystal?
By the existence of crystal.
Yes.
Well, if it's a two-dimensional object, then two symmetries are broken.
I am talking about a three-dimensional crystal, a solid, right? A piece of so solid, a block of iron, if you like. Okay, so it has a crystal structure, and this crystal structure, for sure it breaks Lorentz boost symmetry, because
Mhm.
you are in a medium, and
Mhm.
also it breaks translational invariance, right? Because
Mhm.
you have lattice points and there are gaps. Also you have rotational
Gravitational. Yeah.
symmetry breaking, because it does not look the same when you rotate. So all nine symmetries are broken, right?
Broken. Mhm.
So how many modes will be there? Nine modes. And in
9
fact,
nodes.
when we say that sound is longitudinal wave, that's true only for fluids. In solid, sound can go in transverse direction as well. So for every direction, x, y, and z, you have longitudinal component and two transverse component of vibrational
Mhm.
modes. So in total you have nine different modes of vibration, and these are gapless modes if the solid is infinitely large. So yeah, so you have these nine Nambu Goldstone modes for the spontaneous breaking of nine symmetries in solid. So summary so far, and this will be the end of the first part of my talk. Those of you that are tired and think that it's getting too technical, and indeed it will get technical in the next part, for them it's the summary so far. After that you are free to leave. So summary: symmetry gives a handle on otherwise overwhelmingly complicated problem. Think about a problem is in finance, in e- economics, or climate change. Those are much more complicated problems because they do not have symmetry. And thanks, in physics we have a lot of symmetries, and it makes our life simple. Symmetry is the reason why there are many solutions for a given system, because well, the symmetry of the problem will be reflected in the solution. You expect all different solutions, and one solution will map to another solution when you make a symmetry transformation on the solution. So as we have seen that physical laws have certain number of continuous and discrete symmetries. Symmetries of nature are sometimes approximate, and continuous global symmetry leads to conservation laws, which is Noether's theorem. And finally, the spontaneous symmetry breaking of a continuous global symmetry leads to gapless modes. So by this I would like to end the first part of my talk. So any questions so far? So I would like to take a small break for water before I start part two, and meanwhile you can think about your question. Okay, thank you. Hello, is everybody back? Kamrul sir,
Yes.
are you
Yes.
there?
I am there. Yes.
So since it's called virtual coffee, I thought that without real coffee it does not make sense. So I
Exactly.
made coffee for myself just now, and I will have it while I give the talk. I hope you also have your coffee, or
I
it's
also
too
had
late
it.
for you.
And now
Okay.
I also had it. I also made my coffee.
Okay, I have a
Okay,
question.
now I would like to hear questions on the
Partho
first
want to
part.
ask you something.
Yes, sure.
So in the example of the solids, you said 9 symmetries are broken.
Yes.
So I can count 3 for the translational symmetry, 3 for the rotational symmetry.
Yes.
So 3 are for the Lorentz boost. Is it because that for the Lorentz boost you need to specify
Solid is a non-relativistic system, so you might even call it the Galilean boost. Yes.
So is
Yes.
it because we need to specify the direction of the velocity and also the
Yes.
value of the velocity?
Yes. So right, like the modes, if the modes are moving in different direction, you don't call it the same mode, right?
Okay, so for the direction,
namely a vibration in an arbitrary direction might be expressed as a linear combination of a vibration in three directions, right? It's like an arbitrary vector r can be written down
Resolved
as
into
a
3 component.
yes. It's just that.
okay, I get it. Thank you.
Sir, I
Welcome.
had a claim before
Yes.
asking a question.
Yes.
Sir, this year scientists have found hard evidence for a third kingdom of particles, and they claim that if you create a toy universe, one with only 2 spatial dimensions instead of our familiar 3, the rules of our particle behavior change. And
Yes.
in this 2D universe, the rules of topology allow for the potential existence of a third type of particle, the anion. And does that mean that it
is
will
correct.
break any symmetry in 3D spacetime?
Well, a 2D world is a 2D world. You have to look at the symmetry of that particular world, right? So in particular, the rotational symmetry there is just rotation on a plane.
On a plane.
Right. So the symmetry
It is broken.
as far as space-time symmetry is concerned, the symmetry there is much less. But you have weird things happening, like the notion of spin is vague, because we know there can be fermion and boson. You can either have half integer or full integer, right? Fermion boson. But in in 2+1 dimension, you can also have fractional spin. So spin, yeah. So those sort of things happen in two dimensions. In 2 dimensions also, gravity is not a dynamical degree of freedom. The lowest number of dimension in which gravitational waves can exist is 3. Beyond three dimension, in less than 3 dimension, gravitational waves do not exist. Okay, so 3 is the lowest number of dimension where gravity, dynamical gravity exists, and that could be one way of thinking of why the number of dimensions is 3. Number of dimensions of space is 3 and not 2, because we have we have gravity. It's some sort of anthropic explanation, if you like. More questions?
I had a
Yes, sir. I
question.
had a question about. Okay, you go
Yeah, go
first.
ahead.
May I add a thing, please?
Yes.
Can you allow the question in the end so that the flow doesn't break? I think otherwise, I'm leaving up to Rakib.
Well, I
decide.
mean, this particular moment is the end of first part. So
Okay,
I would
okay.
like
See.
to finish this, and then the next part is more advanced. So I would like to finish here
This
some
part, okay.
questions. Yes.
Sir, sorry for
So
interfering, but okay, you go
I
first.
was
Sorry.
think. Thank you. I was thinking about the global symmetries, and you mentioned that the Lorentz symmetry is a global symmetry. But like, as we know that in terms of thinking of in terms of transformation, like as we know that we use Lorentz transformation only in the absence of gravity, only in a special relativistic case. So is it global in that sense that when you have
No,
curved space-time,
global meaning you are transforming space and time, right? As I showed by, it's a linear transformation, and the transformation parameter is the velocity v, right?
yes.
And this velocity v is a constant. It does not depend on x, y, z, and t. Okay, whenever your transformation parameters do not depend on space-time coordinates, it's a global transformation. Okay.
It's also true when we have this curved space-time. The Lorentz transformation matrix will still be
Well, in curved space, you need to make a Lorentz transformation will make sense only locally, right? In a
so
given
it's not a okay.
point.
That's
So
exactly what I was kind of thinking.
all these things, they have to do with gravity, and this is more advanced topic. I would love to answer your question, but not now. All right.
Okay.
Okay.
Thank you.
So if there are no more questions, I would like to move on.
Sir, I had an inquiry about gapless mode,
Yes.
and you said that in gapless mode, it may occur in any infinitesimal energy. And does
Yes.
that mean that it can break any quantum principle, like Max Planck already claimed that wave
Well,
packet of energy should be finite?
that's a good question. But as you know that if your energy is h cut omega, that is a quantum notion, right? But no one tells you how small omega can be, right? That's where you go. They're still quantized, but you can make the gap between each quanta to be as small as you like. You understand, right?
Okay, sir, I got it now.
So, okay, now I would like to move on to transformations that are not local and not global, namely local symmetries that we also called gauge symmetries. Now, I would like to tell you and why and what are these gauge symmetries. Okay, global transformations do not seem feasible in practice. If you want to implement this change in real life, not mathematically, it does not seem feasible, because how can you implement a change everywhere simultaneously, and no signal can travel faster than light, right? Whereas you want to make the same change everywhere at the same time. So it's not feasible, right, in practice. But then you might think that, okay, what is feasible? That something that is feasible is a local transformation, namely you make a different change in different points of space time. Those are called local transformation, and those you can do, because you don't need to send signals faster than light to tell someone what change you want to make. Your friend might make his or her own change. You can make your own change transformation. So these are local transformation that does not have to be the same everywhere in space time. Okay, so yes, so we have argued from aesthetics or some logic that local transformations makes more sense from practicality. But then we see what it means if we take this notion seriously. Okay, so take, for example, the local internal transformation of the complex field that I wrote, that now you make phi goes to phi prime, and that's a rotation by a complex phase e to the I alpha, where you now make alpha as a function of x, y, z, and t. So you call it a U1 phase rotation. Now it's a local phase rotation that preserves the norm, because once again the norm of phi will not change by this transformation. And norms are important when you are doing quantum physics. That's why when we have a field or wave function, we make such change that the norm does not change, because norm has a physical meaning. Okay, you don't want to change the physics. So these are actually equivalent mathematical description of the same physics if it is a symmetry. Now we have to see, it is actually not a symmetry of the wave equation, right? Because when you move phi to phi prime, then you have this phase factor, which is a function of space time, and the differential operators will act on this alpha and give you some extra terms. Because of those extra terms, the equation will not be symmetric. You will have some wave equation for phi, but you will not have a wave equation for phi prime. So for sure this is not a symmetry. But then you can ask, is there a way we can recover this symmetry? The answer is yes. You can recover this symmetry if you add to the system one more field that we call a gauge field. A gauge field is a field when that you can introduce to recover a local transformation, which when you had the global version of the transformation was a symmetry of your problem. Now by adding an extra gauge field, you see that you can make the wave equation symmetric under this local phase transformation. And I don't want to go into the mathematical details. These are written in books of Ryder, for example, that this gauge field is identical to electromagnetic field. Okay, for every practical purpose, there is no way you can distinguish this from electromagnetic field. So you see that you can predict the existence of electromagnetism just for symmetry principle, right? That you said that I had some global symmetry and it does not seem feasible in practice, and I want to make it local. There you go. Immediately you predict that electromagnetism should exist. Now you might say that this phase rotation was a mathematical symmetry. Okay, now I give you an example that is more down to earth. So take the Poincare transformation. I forgot to mention you, Poincare transformation is the combination of the global transformation I wrote for you, the space-time translation, the rotation in space, and the Lorentz boost. There are 10 10 symmetry, 4 translation in space time, 3 rotation, and 3 Lorentz boost. Combined, they make what we call the Poincare transformation, and all these are global transformation, and you want to make them local. Namely, you want to make different space-time translation at different points. You want to make different special rotations at different points, and you want to make different Lorentz boost at different points. And once again, this is not a symmetry of the wave equation, right? As you realize that the parameters are functions of space-time, and you will have bunch of terms that when this differential operator acts on the, it would be a symmetry if all the parameters were constant, but now they are not. The wave equation will not be satisfied. But once again, you can recover the local Poincare transformation as a symmetry by introducing a gauge field, and lo and behold that this gauge field is identical to what you call gravitational field. So you can predict that gravity should exist just from the fact that in nature you see Poincare symmetry as a global transformation, and you want to make it local, and you are forced to have gravity. Okay. Last but not the least, you have the Young-Mills theory. You might consider a multiple of fields, say two complex fields that rotate internally among themselves. So you can have a non-abelian unitary rotation. This is a group theory term. Basically, you can have a vector and you can multiply it by a unitary matrix U. So you make the unitary rotation such that the norms do not change, right? So as we know, unitary transformation preserves scalar product. So we don't want to change the norm in a quantum theory. So the wave equation, the local symmetry can be recovered once again if you make this u a function of space time. You can recover it by introducing gauge fields, and look, you can have a configuration such that these gauge fields will behave like the weak and strong interactions. So not just electromagnetism and gravity, from symmetry principles you can also predict the existence of weak and nuclear like forces. These are called Young-Mills theories. So I I make a summary of the gauge symmetry. So as you might have realized, gauge symmetries are pure mental construct based on aesthetics, right? I just wanted to make local symmetry because it looks good. So a gauge symmetry actually reflects redundancy in description of physical reality, because once again you want to make different transformation in different points of space time, and you want to call it a symmetry. So for sure you are having more in your theory than you should have. So it's actually a redundancy, and you can completely get rid of this redundancy to describe your physics without this local symmetry. And that's why local symmetries are fake symmetries, you call it, because number one, that physical observables are always invariant under local transformation. Just like a solution that you have in a, like in ferromagnet, right? You have one domain and the next domain that they look different because the symmetry transformation transform one to another. That is always the case for global symmetries. That's why global symmetries are genuine symmetries, they're not fake. But you have nothing like this for gauge symmetries. Gauge symmetries are fake because on something that you can any observable does not change under gauge transformation on. And in it, put in a different way, you can describe your physics without mention of this local symmetry at all. That's why these are our mental constructs. These are fake symmetries, but this is the most useful and most elegant redundancy we ever had. It's fake symmetry, it's redundant, but when you take it seriously as a physical principle, you can predict the existence of fundamental forces. Okay, so you should keep in mind all I said. Finally, it seems that Keats was right when he said that beauty is truth, beauty, that is all you know on earth, and that is all you need to know. You just need to know the symmetry and you can predict what forces are there, right? So it's extremely powerful, the gauge symmetry as a tool. Okay, so we are going towards the end of the lecture. I will now talk about symmetry breaking for a gauge theory, namely the Higgs mechanism. So example one, if you have a conductor, inside the superconductor, you might think of this superconductor as a condensate of Kuiper pairs, right? As you know. So this condensate is charged condensate, and you can create a Kuiper pair out of this condensate, and so you violate global conservation of charge, and that's actually the breaking of U1 gauge symmetry. The fact that the normal material converted to a superconductor, this state, this ground state, which is a superconductor type 1 state, it spontaneously breaks the U1 gauge symmetry. So, and as a result, since if the symmetry was local, there would be a Nambu-Goldstone boson. But since the symmetry is gauged now, and for U1 gauge symmetry, you have the corresponding particle called photon. The photon swallows the would-be Nambu-Goldstone boson and becomes a massive photon. So inside a superconductor, photon is not massless. Photon becomes massive, and we know that massive particles cannot mediate long-range forces. They can mediate short-range forces, and that is precisely why you have the Meissner effect, namely the magnetic field can enter into the superconductor for a very small depth called the skin depth, perhaps lambda, right? And you also have the peculiar electrodynamics of superconductor, precisely because you have massive photons that arises from the spontaneous breaking of a U1 gauge symmetry. Next example is the Higgs mechanism in electroweak theory. In this case, you also have something like the Cooper pair condensate. You call it a Higgs condensate. There is a soup, if you like, of the Higgs field. It takes an expectation value, so we leave in the soup of that particle. As the universe cools down from Big Bang, we have this phase transition, and Higgs creates a condensate. Okay, so this condensation of the Higgs breaks the Young-Mills symmetry down to a U1 symmetry. So in this case, you have three broken symmetry, and three broken gauge symmetry will give rise to three massive photon-like things, and these massive things are nothing but the mediators of the weak forces W plus, W minus, and Z. The reason why weak interaction is short range is because the mediators W plus minus and Z, they are massive, and they are massive precisely because of the Higgs mechanism. Okay, but the there are just three broken symmetries, so three of the fields become massive. The photon does not get a mass. Okay, and that's why the photon remains massless, and the massless photon mediates long range force. That's why we see electromagnetism in everyday life, but we don't see weak interactions in everyday life because they're short range. Okay, so a teaser for you. So we have learned about the Higgs boson in 2014. They said they found the Higgs boson, and I also talked about the Higgs condensate, right? So can any of you tell me what these things are? They the same, or what do they mean? The Higgs condensate and Higgs boson. Any idea?
The Higgs condensate is the wave of the Higgs field. Higgs boson is the excitation of the Higgs field.
That's right. So Higgs are actually two complex fields or four real fields, right? So it takes an expectation value, namely in the ground state, it has a non-zero value, right? So the Higgs condensate is the non-zero value of the Higgs field that it takes in the ground state. It's like the surface of the water. You can have certain height of the water surface. You might think of it as the value of the condensation. So, and then you can also have fluctuations on this expectation value. And the Higgs boson that we saw in CERN is actually the fluctuation on top of the soup of Higgs. So there is a soup of Higgs, and this soup can fluctuate, and that fluctuation shows up to us as a as a particle. So Higgs had 4 degrees of freedom. 3 of them were captured by the W plus W minus and Z, and they became massive. And the fourth degree of freedom remains as the Higgs particle that we found in 2014. Okay. Now, I would like to move on to more advanced topic, just a few words, but I will not go into details. Just one slide to tell you what are the open questions related to symmetry and all that. So I already told you about the Poincare symmetry. That is the symmetry transformation that combines space-time translation, spatial rotation, and Lorentz boost. There is a theorem called Coleman-Mandula theorem that if you look at a symmetry of particle physics, you cannot have more than Poincare symmetry, where the larger symmetry uh, is a superset set of Poincare. Namely, Poincare symmetry cannot be a subset of a larger symmetry under certain assumptions. This is called the Coleman-Mandula theorem, and there is a loophole in this theorem. Namely, it does not work for supersymmetry. What is supersymmetry? The quickest way of understanding supersymmetry, just like Lorentz transformation helps you think that the world is four dimensional, not three space and one time, but space time combined makes one four-dimensional space time. You can think of it supersymmetry as additional dimension, but those dimensions are fermionic. Just like in ordinary dimension, you can take a length and draw square of that length, and that has a non-zero area in a fermionic dimension. If you take a length and you draw an draw a square of that length, that area of that square will be zero. So that's what you mean by fermionic dimensions. But you might think of a larger space-time with fermionic dimensions, then that symmetry will be called supersymmetry, and this seems to be allowed by Coleman-Mandula theorem, and we love this symmetry because this symmetry solves many of the problems, or the so-called problems, that we have in modern physics. And when you want to gauge this symmetry, like make this symmetry local, you have some theory called the super gravity theory, and super gravity theory has also many nice features, namely the normal gravity theory without super symmetry seems to have a problem with finite values. And in gravity theories, it seems that you don't have those problems of infinities. At least they're not as bad without a- at least they're not as bad as those problems that you have when you do not have supersymmetry. There is also an attempt called grand unified theories, or in simple GUT. They try to unify all the non gravitational forces, namely the weak force, strong force, and electromagnetic force, in a simple in a single structure of a larger Young-Mills symmetry. Okay, so, and those theories are also nice because you have unification of three of the fundamental forces. Then finally, you might also think about gravity, right? I did not mention about gravity at all, but we do not actually have a well accepted theory of quantum gravity, and it seems that gravity might be considered as a spontaneously broken phase of some other theory that has particles, massless particles with higher and higher spins. Like for photon we have spin 1, for graviton we have spin 2. Likewise, you can have higher and higher spins, but those particles we don't see in real life, because probably those particles are heavy, so heavy that we cannot produce them in lab. And the, those particles could be heavy precisely because there was a spontaneous symmetry breaking. Those particles were massless also, like the photon and graviton, but then because of symmetry breaking, they became massive, and now we don't see them. Just like 100 years ago, we did not see the weak W plus W minus and Z, right? It could be something like that. So, and I mentioned this last thing because I work precisely on this kind kind of problems, that how can we understand quantum gravity by understanding higher spin gauge theory. And there is also a very important thing that I did not mention, but I would like to end my talk with this last thing, that in our universe, I told you throughout my talk many times that if there is a symmetry, you will have all the solutions that are allowed by symmetry. So it seems that the laws of physics are invariant under matter antimatter uh, mm, exchange. So when we first learned about antimatter, it was believed that some of the galaxies are made of matter, some of antimatter, because matter antimatter cannot exist in the same place. They will annihilate. But it was believed that some of the galaxies are made of antimatter and some with matter. When they collide, they will annihilate. But it seems more and more that we don't see antimatter, or we don't see galaxies made of antimatter. It seems that we have overwhelmingly more matter than antimatter in our universe. And just like you see all possible orientation of the ferromagnet, and you should see it because they're allowed by symmetry, and matter antimatter both are allowed by symmetry, but we don't have a concrete answer to why in universe we see a dominance of matter over antimatter. These are open questions. I am not an super expert in the last topic, but Talal can talk about it if you want to hear about it. He's an expert of the last thing I wanted to mention. And with this, I would like to end my talk and thank you very much for your patience. Kamrul sir is there or not? Hello?
Yeah. So hello, now is the question
Yes.
time. If you have any question, please feel free to ask. Talal is there.
I'll go ahead and ask a question. Actually, I have a confusion about just the definition so in the last part, we began with the definition of, or the shortcomings of the global transformation. If you can go back to that slide. It's probably better if I turn on the video, that it makes communication easier. So it's just about the definition of global transformation. I think it's a different slide, but anyway, because the thing is that the way I understood global transformation is we call the transformation global if we can use the same transformation matrix regardless of any position or any time.
Yes, that's right. But that's also what I said, right?
But when you said about the shortcomings of the problems with global transformation, you said that it's like it's not realistic.
I'm not saying that it's a problem. If you take a symmetry as a mathematical fact, there is no problem in it. But I am saying if you are an engineer, not a mathematician, you might want to
okay,
ask.
I see. Okay, I see exactly what you mean. So it's like if we say that global transformation means it should be the same everywhere, but you can't test it everywhere because it's just too much space. That's what you meant, right?
It's also not just a question of testing. It is also a question that if you say that I want to make this change, now you have to tell all your friends at every point in space to make the same change, and that has to be at the same instant, right? There is no signal that goes with infinite speed, right?
Yes. So there's in a way there's no way of realistically measuring realistically seeing that if a transformation is the same at the same time, because you just can't have those two transformations at the same time and communicate the information. Okay, yeah, that makes sense, but I mixed it up with the other definition. And then there's another thing I was thinking. It's not really a question. It's far back from some of the first slides, but we don't have to see the slide. It's about the translational symmetry of, or it's rather the simultaneous translation symmetry of time and space in case of the electromagnetic field. I mean, we all know that differential equation. And I was just thinking that this is the, independently, the space and time is not translationally symmetric.
It is. I said there are four symmetries, right? So you can make three of them, any three of them to be zero. Say T naught is non-zero and X naught, Y naught, Z naught is zero. That's also a symmetry, right? there are four symmetries. You can choose to make a translation in X, you can choose to make a translation in Y or Z or T or two of them or three of them or all of them. It's up to you.
Yes, but
all of them are symmetries, but you have four linearly independent transformations.
you had another equation where you multiplied like T prime transforms as lambda times T.
This one?
No, I think it was before this, where
You're talking about scaling, lambda T or something.
This one?
the scaling, yes, the scaling one. Yes, this one. So in this one, it seems that we have to make
Can I
simultaneous
make a comment? This is a symmetry of electromagnetism. It does not exist even even when you consider electron. Whenever you have a mass, this sort of symmetries cannot exist because mass is a scale. And when you have scaling symmetry, as soon as you have it, you mean that you should not have a mass. So this exists as a symmetry when you have free Maxwell theory. Pure electromagnetism has this scaling symmetry, but electromagnetic waves in vacuum, they do not need electron, right? You might not care where the wave came from. I did not tell you where this wave came from, but when this wave is there and it's moving in vacuum, it's vacuum, and we don't have a scale. We have conformally this symmetry, and all wavelengths are possible. Yes, now please ask the question that you wanted
so
to ask.
this is so this symmetry would not apply in a massive medium if the electromagnetic wave was going through a massive
This
medium.
symmetry is a symmetry of electromagnetism without electrons, just for pure photon, and this is not a fundamental symmetry of nature. But I said that the symmetry of a problem maps solution to one solution to another. So you take this wave equation, you realize that it has this symmetry. I did not care whether this symmetry is a fundamental symmetry of nature or not. Mathematically, this equation has a symmetry, and I showed you what it means. It means that you should have all wavelengths there. Yeah.
I guess the thing that I was thinking about when I was I was thinking about I was thinking of the simultaneous transformation or the simultaneous symmetry of the space and time, and I was thinking that maybe it has to do with the fact that space and time are the same thing. That's what I was thinking, but I think that now it doesn't. Now it
This is
seems
true
different.
that in a relativistic theory, you cannot rescale space and time differently because they are on
That's
the
what I
same
was thinking.
because they are on the same footing, right? It's like X, Y, Z. T is as good as X, Y, and Z. Yes, that's right. This is because you have relativistic theory, but in a non-relativistic theory, you can have something called dynamical scaling, where you don't have the same transformation of T, same scale transformation for T and X, and that is already true for the Schrödinger equation. Schrödinger equation also has this sort of symmetry, but X, Y, Z, and T, they don't transform the same way. Yeah.
Okay, yeah, that's what I was thinking. Yeah, that was all of my questions.
Thank you.
So, any more question?
I saw something like I see 36. How many do you see now? How many participants?
36 now, because
okay,
there
so
were
out of 36, I heard from just a few, 2 or 3 of them. But how about the rest?
I have I have a question.
Who are you?
I am Hafiz Ahmad Bhuya.
Okay.
Okay. Maybe the question is very silly, but I want to ask it to you. What is the definition of time?
Oh, that's a good question. By the way, there are recent theories that say that time might not be a fundamental quantity. Anyways, I would say that the definition of time is a time is something that helps us to understand changes, right? Time is a notion that helps us to capture changes. So if you have a still picture, nothing is changing there, and there is no notion of time in a picture, right? When things are dynamical, things are changing, if there is a change, and time is a technique, if you like, to capture the change of things. Yes, if nothing is changing, if the whole universe is frozen, nothing is changing, time will cease to make sense. And that's what we say when we say that there was no notion of time before Big Bang. Time does not exist. Time was born at Big Bang because things started to change from Big Bang on. Okay, so I frankly don't know what is time, but my best answer is that it's a trick that humans in, invented to describe change.
And
So,
that change towards increase in entropy
Exactly. At macroscopic level,
level,
that change is
macroscopic.
unidirectional, but it's not, right?
so maybe the time is not a physical quantity. Am I right?
Well, what do you mean by physical? I don't know. We are human beings, and we have ways
No, no.
to think about reality. But I would say that it's a trick that we use to understand change. Whether it is reality or not is a philosophical question. But the notion of time might not even make sense at the very fundamental level. And there are recent theories that also suggest that even the notion of might not be meaningful at the very fundamental level, whereas our physics is formulated in terms of change in space time, and space time itself might change in when you have gravity. Is that at the very deep level of nature, space time does not exist. All you have is information. You have information. The whole universe is like a giant computer where computations are going on, and to have the notion of information, you don't need the notion of space time. It's just some boolean computation going on in a large machine, and only at the macroscopic level you have the fake feeling of space and time. Yes, they might not be fundamental.
So the whole world, the whole universe may be the fake one.
Well, I would not say fake. Look, I mean, if you go to a rural part of the United States, say you ask a farmer if the sun is going around the earth, that farmer will say yes, right? To him, that is truth, and it approximately that makes sense, because when you're looking from earth, you see that the sun is going around. So what is the problem? The problem is that with this you cannot explain everything. Certain things will break down with this model, but all our models are approximate. When Newton said that gravity is a force, okay, that works, but from Einstein we know that gravity is not a force, it's a manifestation of curvature of space-time.
Space
Only
time.
when you are in a weak gravity regime and moving slowly enough, it feels like a force. So the feeling of gravity as a force is a fake one. It's an illusion, if you like. Seeing gravity as a force is an illusion, just like seeing that the sun goes around Earth is an illusion, but approximately it makes sense, right? Approximately, if you are in a certain regime of experience, calling gravity as a force makes sense. But when you go beyond that regime, calling gravity a force will no longer make sense. Okay.
Maybe the
It's
word approximately I want to replace by the word relativistic.
yes, I mean there are also theories that says that Lorentz symmetry is violated at the more fundamental level. By the way, if you do not have space and time at the fundamental level, then of course all the symmetries of space and time will also be gone, right?
Yeah, thank you.
So,
Thank you.
okay.
Welcome. Yes.
Okay, Hafiz.
Yes, sir.
I think it's a good time to stop unless there are more questions.
Yes, you already spoke for more than 2.5 hours.
Yeah.
So you need a break. And it was a really, really nice talk.
Thank you.
When looking for order, finding order in the disorder, it has always been a proposition for physics, and it's a really interesting question. So order means finding symmetry, finding scaling invariance, similarity, self-similarity. And so we made all these connections today. That was a really, really wonderful talk. And we had more than 110 participants today. But of course, with time, people go away. And now we have 37 people. These are real, genuine people, those who wanted to hear physics. And it's nice to have 39 is not a good bad number. It's a good number. They stayed for almost 3 hours. No, so very good. And so with that, I would like to thank Dr. Rakib once again
Thank
for
you too
such
for
a
this
wonderful
nice
talk.
initiative.
And yeah, so now have a break, have a Kit Kat.
Thank you very much. Yeah, you have good night. I think it's quite late there, so you all have a good night, and thanks for your patience. I hope that you learned something from my talk, and I hope that you could see known facts in a different angle. Right now you know why we have sound waves, why we have gravity, why we have electromagnetism, and all that. Right, those things you might not have thought the way I say it.
Right. Excellent. Yes, indeed. And I also think that students enjoyed very much. I'm happy to see Arman is there, and our Sabir was there, and our Partho, he made some good questions. So it's nice to see all this face. And so with that, so thank you once again. So good night.
Good night. Yeah.
Good night. Bye.
Thank you.